Hello everyone, welcome to this course of using artificial neural network to produce prediction maps in GIS environment. Actually, this course is one of the highly recommended technique in literature, especially to predict the spatial distribution of specific target events in specific regions that represented by conditioning factors, as we call it. So the targeted spatial applications using the current course will be, for example, health, like the viruses susceptibility map, noise maps, and infection diseases. Same as if we study complex diseases, like find the potential risk factors and their effects on the disease are investigated to identify the risk factors that can be used to develop the prevention or intervention strategies. And for example, if we work on the hazards like flooding, landslide, geological-based hazards, droughts, air pollution, for example, we are searching for the flooded areas and the contribution factors as well. So as you see here, always we have the target, what we call the response, represented by the events like the slides, like the flooded areas. At the same time, we should have the contribution factors, which is called the explanatory factors, which is called as well the independent factors like the topographic, climate data. In the same time, we can work also on the climate change related to the consequences and the dragging factors again, like the urban heat islands and its relation with the land uses. Habitats like increase specific type of species in certain areas and predict its relationship with the surrounding conditions. So here we have dependent and independent factors. So that is the usual behavior of the regression methods, for example, the bivrate methods that we present in different courses. So this course is an extension of the courses that we applied before about the regression behaviors or studying the relationship between the independent and dependent factor. And at the same time, also this course can be taken to minerals explorations, urban planning, cost prediction, and the land suitability analysis. Along this course, I will be with you. My name is Omar Althuwaynee. I have a PhD in the Geographic Information System and Geomatics Engineering. Also have wide profile of application for spatial analysis, hazards, and etc. So I will go through the course content and run the required code step by step, and you will find the data set, code, and some literature that will help you to understand the procedure effectively. In addition, I will always be waiting your questions either in the Q&A section or via email. So feel free to start the course using the data and apply them, follow the videos, pause them step by step, take your time. If you are preparing manuscripts, if you're preparing a project, there always be this method using artificial neural network is one of the advanced methods. At the same time, you have the previous videos that it's related to the regression and also the bivrate methods. So first we start with introduction to the artificial neural networks. Especially here we will work on using the R environment, R programming environment, and QGIS, which is both of them open source. There is nothing like a commercial software is needed on extra things. So the code will be provided data, and we have those kind of open sources available. So you just need to download them and start effectively. In the QGIS software, we will start with the data preparation. So here in this application, we will use the landslide data, which is represented by points and polygons. So both of them possible. So I will show you how to deal with if you have just points or you have the polygon data. As we mentioned for the previous applications, you may use all of the examples that we mentioned about the health, about the hazards, about the urban planning, in base of that you have a point representation or, for example, a raster pixels. So all of those kind of applications possible to carry with the current course. So also we'll continue with the QGIS to produce the training and the testing data using the grid-based method. Actually, as you see here, the grid-based method, which is using the pixels, pixel to pixel, if you go through the literature, most of the work that done by GIS for the statistical analysis are using the pixels. In the same time, you may use the another way of the response representation, like the slope units, which also I presented this in a different course earlier. So either you'll see if the grid based distribution of your points, it can be a pixel based, every one point represent one pixel, or maybe you have a polygons, every one polygon which has a specific area, so this area represented by the pixels. So if you have, like, for example, 500 meter and you have a pixel 500 square meter area for one event, and you have a pixels, for example, 30 by 30, so you will have like almost like every pixel you have like 100 square meter, so you can see within this 500 square meter how many pixels will be covered, and this relationship can be found as well in the QGIS. After that we will see also how to train it, but why I use the QGIS, because this is a quick tool that I developed earlier. So I will put the code that it will run inside the QGIS, so you just need to follow the instruction, put the code, put the tool inside the QGIS, and then everything will be run automatically. And as we said, this course I have prepared for so long, and it's heavy and has a lot of things for you provided. Everything can be found in the attachment section. When we move to the RStudio, now we make the environment settings. We'll import the training, validation data. We do the scaling. At the same time, if this with the continuous data, but with the categorical data, like aspects, land uses, land cover, in this way, we need to convert those data from the categorical data to numeric. And I will show you also how to convert them from the categorical to numeric in the code. Then we will run together the neural net function with the training data. So we will learn how to plot the function network, how to do the pairwise neural net model result, that the pairwise relationship between the experimenters and the response data. So if you have the flooded area, or if you have the landslide areas, if you have the mineral potential points, and what is the relationship with the other factors, land use and topographic maps. Also, at the same time, we will study the generalized weight. So we get the weight for every factor. If you study the regression, every independent factor like elevation or slope, you have the general weight for the entire factor. But in the artificial neural networks, you will have the weight for every pixel, inside this slope unit. So we will plot this, and you will see as well wonderful outputs that can be reflect a clear image about what is happening with the data relationship between each other. At the same time, we will move on with finding the variable importance. So here, this is an extra step, because in some students or in some literature, they like to see which one is more important. Is it the slope? Is it the land use? Is it the elevation? Is it the roughness? So which one is more important in this case? As we said earlier, we will take the generalized weights inside every pixel, but what about the general weight for this entire factor? So this step also we will do it with the extra codes. One important thing as well, we will use the sensitivity analysis. Sensitivity analysis simply will be if you are using one independent factor, like for example you have 5 independent factors. You have the elevation, you have the slope, you have the land uses, you have the roughness, you have the topographic wetness index. So 5 factors, yes, they are working together to produce prediction map. But what about if you use just one factor independently, or if we use one factor and for example 10% of the others? So it's a sensitivity analysis, it's a selective. So normally we are using 5 factors or 4 factors. We are just subtracting one, adding one, subtracting one, adding one, like, trade off. But here, this is not need to do. This is the sensitivity analysis can go further. So you are having one factor and 20% of the rest of the factors. or 30 or 40 or 50% or all of them. So you will see, for example, if this elevation is very important, it will drag the rest of the data with it. For example, if the elevation show high importance, you will see that even if you add the other factors, it won't affect too much because it's very strong. But if you have the elevation, and then when you continue to add the 10, 20, 30% of the rest of the data, you will see the behavior of the elevation change. That means it's not very strong predictor. In addition to this, we will continue to go with the prediction results, the validation, which is the classical way of using the area under the curve of the ROC plot, which is also one of the proposed method that you study how much the cross validation or the tabulate validation between the data, the training data, first training data with the prediction, and then you take it as unsupervised. So you have the prediction when you do the training using the training data. After that, you have the testing data. So you test the model based on there is some data you are saving it. So this data that you saved, it measure how much you can predict those data. So it's supervised. So you can see that, okay, I have some witnesses. They are waiting, they are hiding. So they want to see, did you represent them very well without using them? Okay, so if I see that, yes, most of those points that are hidden, they are well represented by this training model, we'll come and match them. So when we match and we see a very nice agreement between the data that we hide and the data that we predict as if they are there. After that, we see if the model behave nicely, we can move on to use the rest of the areas that it doesn't have any events anymore. Our all data will use training and testing, and there is the modeling, the last part, which is using for the prediction. Okay, so there are some areas that you don't have a landslides data about them, or you don't have flooding data, but you want to predict whether that area can happen because you are using the conditioning factors that it leaded to the events happen in a different area. So we will see how much this kind of data, the landslide data or the flooded areas, or as we said, the target, how much it was enough to train the model to go and behave well in the area that it doesn't have guide anymore. It doesn't have the dependent factor, like as we said, the events, the viruses location, the minerals, boreholes. And then we will export the final prediction map as raster. In the end, you will have nice maps that it will reflect, what we listed here in the table of content. So here, all this process, as you said, it will just using the QGIS and the R only. So the expected outcomes of this course, first, we will have the neural network plot, as you see here, are using those factors, and this is A, B, C, D. Later I will explain they represent the categorical data when we convert them to numeric. And you see also on the right side, just the training. So there will be the entering data with the explanatory data, as we call all the independent factors. After that, we have the second row will be, this is the hidden layers. I have 5 hidden layers here. After that, we have just one output, and you see this is the one, the blue one, it's the bias. The second output, it will be represent for the nnet package. That is the function that is the classical way that it's been used by too many authors earlier. But why we are using the neural net? Because it is able to show us the tree or the plot easily. But here, this one, we use an external code. As you see, also the behavior here, it's almost similar. It has a little bit differences with the plot. And you see the dark colors of the lines here, which is represent that the weight, how much it's heavy or how much they contribute here. So if it's more bold line or the thick line, how much this factor is effective in this plot. Then we will have the generalized weight plot. As we mentioned, the generalized weight here, you have, for example, the first plot in here. So you will have the training data and the conditioning factor like topographic weightness index, TWI, or the SPI, roughness, elevation. So I can see here, this is the 0, and whenever we see that there is a data above and below the 0, that means it's contribute in this factor. So this factor is important. Whenever we see that most of the data, most of the training or testing data, it's just within the 0, that means this factor is not useful, is not effective. That means the weight of this factor go around 0. Or if you see the weights on the y-axis, I'm talking, if you see the weight is passing above and below the 0, so that means it's contribute either in the positive way or in the negative way. Also, so you will see in the SPI and so on. And there, when you go and see the A, B, C, D, this is represent the aspect actually. When we converted, so in aspect we'll have just 0 and 1. If you see that you have too much points within the 0, okay, that's mean no. That's mean if you have an aspect, for example, 0 to 15 or the 25, that's mean north, east. So north, east, 0 to 20, we are giving this as A. So when you say A, 0 and 1, 0 will represent there is nothing, and those points, that's mean the entire raster doesn't have this northeast. We are northeast, just looking for the northeast. Whenever there is a northeast, 0 to 15 to 20, there is value of 1. So if you see here the value of 1, it's very limited numbers. That means it's not good prediction. The same as also here with the C. C also, it is in different aspect, which it will you move from 0 to 360. We'll show you everything along the course. Also, there is a pairwise plot. So pairwise, actually this code is very nice. So what it's showing the relationship between the factors themselves. So if there is independent factors, for example, the last row here, this is the prediction. This is the prediction. So when you see the prediction relationship with the others, for example, with it's come with the elevation, you can see that the prediction is passing, the x-axis is the elevation data. You can see always is from 0 to 1 because we scaled the data, and here on the y-axis it's the prediction. Okay, so you can see also the relationship, whether it's linear, non-linear. This is the red line, it reflects the relationship, and if you see this red numbers here, it show you the significant. Okay, and also if you have it's a linear model, you will see also high numbers. Also we'll discuss this along the course. Here we talk about the general weight of the factors, which is this is an extra, because in neural network, whenever you change, if those factors actually they are not very high contributors, whenever you run the neural network as a black box, you will see there is different behaviors. So this is an extra actually step. I'm not recommended very highly, but it's also is nice to have a look, because if the factor is very strong, always you will see it's presented here. But if they are not too much strong, you will see they are changeable. So if you see here, for example, we have the elevation, it's coming in the positive, and it's the value from 0. The colors, for example, this one in the minus, and this is in the positive, and this is in the negative, sorry. So you can see here is the maximum, it's coming the weight, so you can understand from the scale. So this is, for example, it's less than 0.25. Okay, so you can see all of them, they are close to each other, they're not too much important, they're less than 0.25. But here, if you see, for example, the curvature, it's coming on the opposite, and it's -1. Also, there's very nice explanation the behavior of the conditioning factor with the target. Here we come to the sensitivity analysis. This kind of output, for example, we have the split. First, let's say, for example, elevation again. If you see the elevation value from 0 to 1, why? Again, because we scaled the data. All of the data you see here from 0 to 1, we scaled the data, then we can compare them to each other. So from 0 to 1, so when this elevation, it starts with the 0, that means it's only the elevation acting here. There's no other factors, just the elevation with the target. So you can see the behavior. When the elevation, low elevation, it is almost linear with the events. So in the high areas, we have high prediction. rate or the response here. But is it very strong predictor? I don't think so, because when we add rest of the data inside, within like 20% of all of the data, we put them together, or 40%, you see when there are 40%, it becomes green. So this green, it's the 40% of all the predictors in addition to the elevation. Okay, so you can see is the predictor become not too much effective. When we can see it's high or low, no, it's almost stable, so it's not very strong. It's almost like turned off the effectiveness of the rest of the factors on the elevation itself. While if you see in the slope actually one of the main factors for landslides, which is in some countries they are taking the slope only as a guide, because if there is no slope, there is no landslide. So you can see there is the behavior of the slope. So if the actually the data that we have, almost like there is a specific range, always you have the landslides, but after that, when the slope become very high, we don't have too much events. So if you see, almost reach to zero. You see the zero here, almost after the 0.5. That's mean later on I will show you the equation to convert back, or to take then this number back. For example, 0, it was 0, but 1, how much it was, for 60 degrees or something. So we how much the 0.75 in the scale and the original data. So I give you the equation of the scale, so we can convert this 0.75 to the original data. Then you can see that, okay, if we have 0.5, the relationship become almost linear. There is no much prediction here. Then how much this 0.5 reflect on real life? Is it 30 degrees, 40 degrees? So we will learn this. That's mean before this 40 or for this 40 or 30 degrees, we have very nice prediction. But after that, it's not important. So this is very good. At the same time, if you see in the slope, while we are adding more factors, as it starts from 0, or we add the others, the slope behavior is not affected. It is not affected by the others. That means the slope is very strong. The slope is very strong. It can overcome all the other factors with it. Okay. Why we got this data actually, because I run this analysis based on the slope unit, which is logically slope unit. We create the database on slope, so everything is following the slope more effective than the others. And this is code also nice that you can zoom in more and you can just select 1 or 2 factors. Now, if you have if you see that the curvature or the roughness, they have not much effectiveness, and you want just to choose the elevation and the slope, so you can just present them independently. So you can see their behavior in more zoom, and you can increase the scale, you can increase the y-axis, and you can see the behavior more clearly. And also you can increase the split, so you can say I want to see every 10 quantile of the other of the data. This splits based on the quantile actually. You want to see like every 10% what is happening with the data. If I add 10% of the rest of the data with this specific factor, how much it can affect the factor on the prediction accuracy. So before the last step, we will find the area under the curve, which I'm sure most of the researchers that working on the natural hazards, they like to see the area under the curve, which is one of the most robust methods. Okay, so this one we will run it based on the testing data, and also for the validation for the data for the rest of the areas that we don't have events there. So it is purely the prediction using this model. And the last, on the final map, it will be the prediction map. So we will produce this prediction map as well using the results come from R. Then from R we will export this result to QGIS. Worth to mention here, we will not have equation like the regression. The regression analysis, we got the responses weights, and then we multiply using the regression equation. But here we will not have an equation. There is no equation actually recommended inside the artificial neural network. But what we have the weight for every pixel. So the weight of every pixel is there. So we will convert those weights, that is usually from 0 to 1, predict to us from 0 to 1. 1 is 100 and 0, so we will convert this as raster and we will plot it. So you will see that whenever the area come nearer to 1, we'll multiply by 100, so it will be like 90, 75. Then you'll see this is a high susceptible, can guide us to high prediction. Where the areas that coming to the low, so it will be less. As you see here, this is actually I'm just printing the gray. So if you see the dark area, it's just the valleys, that there is no landslides there. And whenever you have the white, that's mean almost you are reaching to the 1. You can see the slopes, the susceptible slopes. We will do it in the more professional way, actually using the QGIS later. So I hope we will have an interesting journey. Artificial neural network is an effective tool, actually using the neural net, and the code is there, the materials are there, and the explanation will be step by step using the code. So without losing more time, this is Omar Althuwaynee. Thank you, and let's begin.